Okay, ladies and gentlemen, welcome to our second talk in the morning. The speaker is
Etienne.
Etienne Desquith from Société Mathématique de Côte d'Ivoire. He is an expert in functional analysis, harmonic analysis, group theory, and generalizations. Today, he is going to talk on from Banach algebras satisfying the finite n-dimensional square property, FDS underscore in property to the concept of projection Banach algebras. Let's welcome.
Thank you. I'm very happy to. I would like to thank the organizers of this ICBS conference 2025 and for having been invited to attend. So the title of the works from Banach algebra satisfying the finite n-dimensional square property to the concept of projection Banach algebras. Okay. So for the subject, it takes its roots in a result of Cohen saying that if a Banach an infinite dimensional Banach algebra has an approximate identity, then its square equals to A. We then raised the question of about what happens when A is not is without approximate identity. There are some errors, but I will skip them. So our goal has been since then to provide on an arbitrary Banach space the adequate product turning X into a Banach algebra R that fulfills dimension of A square is greater than 1 and less than some integer n and satisfying square A2 different from A. The organization of the work will be in 4 sections. First 2 and 3 sections will deal with dimension of A2 equals 1, 2, and 3. And in section 4, we will try a generalization of the algebra found in section 2 and section 3. First section, we deal with dimension of A2 equal 1. Let me say that the first time we considered this hypothesis in section 1, we were afraid that it could be some crazy idea. But fortunately and unexpectedly, it gives rise to 3 families of Banach algebras, 2 among them being composed of nilpotent Banach algebras with admitting the integer 3 as order of nilpotency. Definition: an algebra such that dimension of A square is finite will be said to satisfy the finite n-dimensional square property, FDS property for short. Okay. Now, if we consider A an infinite dimension Banach algebra such that dimension of A square equal 1, then there exists a non-zero E in A and a continuous bilinear form B on A times A such that the product of this Banach algebra satisfies xy equal bxy times E. The associativity condition in A would yield the relation 2 here, and making x equal E in relation 2 gives the relation 3. In the other hand, the linear form S and T defined by S of x equal BEX and T of x equal BXE provide clear relationship between the bilinear form bxy and the value of the constant complex number bee. So it appears that the solution of our problem closely depends on the value that bee may achieve. Let's consider the first condition of bee equal 0. If it is so, then the E belongs to the kernel of F and kernel of S. Moreover, uh, it follows that then S is identically 0 and EX equals 0 for all x in A. Similar argument when Z equals E in relation to leads to T identically 0 and XE equals 0 for all x in A. Therefore, we have an algebra that satisfies system delta 1 A squared equals CE by the product, EA equal AE equals 0, and A power 3 equals 0. That means that XYZ equals 0 for all X, Y, and Z. The question now is, which product on a Banach space X provide the algebra A which satisfies the above properties? The answer will use lemma 1-3, which essentially say that there is some E non-zero in X, F, G, H linear forms on the topological dual of X, and HE equal 1. Lemma 1-3 and the comment leading to the constant BEE satisfying condition 1 BEE equals 0 lead us to our main theorem in this section, which says that let X be Banach space and E an element of E, X, F, G in X prime be such in lemma 1-3, then provided an appropriate adjustment of the norms of F and E, the operation xy equal fx g y e yields on this a Banach algebra denoted AEFG and satisfying the finite dimensional S square 1 property and the system delta. We have here definition of nil algebra and nilpotent algebra. In fact, not only we have got an algebra which square is dimension 1, but this algebra is nilpotent. That means satisfy an equals 0 for some given n. Example, example AEFG is nilpotent, has order of nilpotent 3, and fulfills the general result that we shall skip. And we are talking about symmetric bilinear forms. The definition of a symmetric bilinear form BXY goes like this: BXY equal BYX for XY in X. So if we take a non-zero element in X, as seen the definition of AEFG, then the equation BCF and BCJ defined here are bilinear forms, symmetric bilinear form, and the map XY equal FX FY E, and BCG of XY XY equal BCG XYE, which is also equal to GX GYE, give rise to bilinear form, but not commutative or something. bilinear forms, and they define an algebras denoted by AEFF and AEGG, which are commutative uh, nilpotent Banach algebras, although AEFG was not commutative. Excuse me, could you recall what is the F and G? I say that it was there were elements of the topological dual X prime of X. So, what is the difference between F and G? F is a topological, an element of a topological dual. G is another element of the topological. Okay. Yeah. And proposition 112 uh, is particular, but because it says that each subset of X which contain the element E is automatically an left ideal of this algebra. And many algebras satisfy this proposition. That's why we call such kind of subspaces idealizing subspaces of A. Now we come to the condition BEE different from zero. And without loss of generality, we may take EE1, then making Z equal E, relation 2 becomes the equation 8 here. And the product given by xy equal tx, tye, with te equal 1 gives an algebra which is not nilpotent, but it is commutative and admits a unique multiplicative linear form, which implies that the Jacobson radical of AET equal of T. Could you recall what is FDS algebra? Okay, FDS algebra. FDS, let me see, the square of any Banach SDF algebra. And okay, when we say that, in fact, here I didn't use this. It's one of the errors in the paper. I didn't talk about the FDSN algebra, which will come in section 2. But algebras I'm talking about here just to satisfy the FDSN property, which means that the square has dimension equal n. Thank you. This is the abbreviation of finite dimensional square. Yeah. Okay. Yeah, it's a finite dimensional square. Okay. So we come now to some comments between nilpotency and Banach FDS1 algebras. The concept of nilpotency in the mathematical literature appears often in the theories of Lie groups and Lie algebras, but it doesn't seem to be the case in the theory Lie groups and Lie algebras. Yeah. It's not the same thing for the theory of Banach algebras. For example, in his book, Banach algebras and the general theory of Banach algebras, Theodore Palmer defined the notion of Nicolan algebras. But in this book, nowhere else in volume 1 of this book did appear some explicit example of the of Banach algebras. Moreover, when we recently Googled, excuse me the expression, nilpotent Banach algebras, the output we received was entirely composed of types in Lie group and algebras. We didn't find Banach nilpotent algebra. So That's why we say that if the comments above happen to prove that no infinite dimensional nilpotent Banach algebra has yet been put in evidence for this presentation, so maybe the problem NP1 and NP2, which are equivalent, uh, can be posed. Does there exist an example of nilpotent Banach algebra outside of the nilpotent family AEFG and AEFF described in does there exist? Yeah, described in this presentation. NP2 is equivalent to this question. Maybe at the end of this talk, somebody will this problem is not so hope that he said RC1 and RC2 are almost same. And we go to section 2 for dimension of a square equal to. Okay, we have some definitions. And assuming that a Banach algebra satisfies dimension of a square equal to implies that there exists bilinear form B1 and B2 and linearly independent elements E1 and E2 in A such that XY equal B1 E1 plus B2 E2. The associativity condition of the product in A yields equation star here and equation 2 stars. Then we consider the linear form Fi and Gi associated to the bilinear form B1 and B2 and defined by the 8 equations. Yeah. Now, putting together equation, putting the Fi and Gi's in relation star and 2 star give the equation EQ1 and EQ2, and it's one of the mistakes because EQ1 and EQ2 are missing here, but they are little transformation of equation star and equation 2 stars, just to replace replace B. Oh, no, sorry. This is here, and equation and just to replace replace equation. Okay, it's one up again a little bit. Yes, equation A star. In equation star, replace B E1 Z and B1 E1 Z and B1 E2 Z by something in G1 Z and G3 Z, and we get equation EQ1 and EQ2. But if we put equation EQ1 and EQ2 together, they provide the system I0, which is here, which can be written in the form of the Kramer type system, My equals C, where M is the 2 by 2 matrix AB, alpha, beta, Y equal column the column vector b1 xy, b2 xy, and c equals small c and d. And all the thing remains to solve this system to find uh, yes, y composed of the bilinear form we are looking for, b1 and b2, b1 and b2. So this can be made first of all by putting z equal e1 in equation 2 and equation 1 and equation 2. It gives another system, one I1. And if we suppose that the determinant, which is here, calculated with A, beta, alpha, and beta, which appears in equation 1 and equation 2. If we define that this determinant is different from 0, then the resolution of I1 gives system I2, which is here, B1 and B2. But this, and again, now if you suppose that, yeah, by taking F1 E1 equal F1 F4 E2 equal 1 and F1 E2 0, which is equal to F4 E1, the determinant is 1, and it gives another system I3 with B1 XY and B2 X2. But these bilinear forms are not given an associative Banach algebra. So we have, with what we have here, compute again the associativity condition, because many things have changed from the first system to here. And when we make this computation and take some additional conditions in relation 1, 2, and 3, we get the result, the final result, R1, R2, R3, where the B1 and B2 in each RI gives associative product for what we need. And taking R1, R2, and R3 will give the first three results of Banach algebras we are looking for. And in theorem 2.5, we get the algebra called A21 with B1 and B2 in R1, and the product of this algebra, xy, P1 xy equal fx, f1x, f1y plus f2x, f2y e1 plus f1x, f2y plus f2x, f1y e2. The second Banach algebra called A22 will have for bilinear form B1 and B2, which are there, and for product P2 x1 xy equals this relation. And the third Banach algebra called A23 will have for bilinear forms B1 and B2. I'm sorry, we are in P4. Yes, B1 and B2 here, and for product the product P3 xy equal what is written there. No, I didn't say it, but the resolution of the first since the first system will give 6 of the Banach algebras with the property that their dimension is the dimension of their square is equal to 1. Now we have 3. It remains 4, 5, and 6. And for 4, 5, and 6, we go back to system 1, 2, and we calculate another determinant, which is -1. And we do all the work we have done in the previous discussions, and we find the right bilinear forms B1 and B2, who gives the algebras A4, A2, 4. For A2, 4 have bilinear forms B1 and B2 here, and the product P4, which is there. Equation the algebra A to 5 has for bilinear forms what is bilinear forms. Yeah, bxy equals this and the other one. And the product is P5 xy equals f1x, f1y e1 plus f2x, f2y e2. Okay. Okay. So, and now the sixth Banach algebra A to 6 has for bilinear form B1 and B2, and the product P6, which is here. Okay, so if we call FDS2X, all the A2K for K varying from, varying from I think greater than 1 and less than 6, we have solved the question for dimension of A square equal 2. But we want to link A21, the first such algebra, to M2 of C, the 2 by 2 matrix of coefficients. For this, call A21 square, which has dimension 2. We call it J21. J21 is a two-sided ideal, and we define the map DS from J12 into M2 of C, and we consider the involution J on G21 on G21, which is a square. And finally, if star denotes the we call a star the natural involution on M2 of C, the composition of the star, the star map and the DS map give the results that we can define a map sigma 1. We can define a map sigma 1. Oh, a map sigma 1, which is, sorry, map sigma 1. Yeah, sigma 1 of x equal f1 to x, f2 x, f1 x, j to 1 into m2 of c. And this is an isomorphism when j to 1 is considered as a Banach algebra in its own right when the product of a to 1 is restricted to this ideal. So this map is isomorphism. And we can construct the over isomorphism from for a to 1, it is sigma 1. We can construct sigma 2, sigma 3, sigma 4, sigma 5, sigma 6, which are listed there. So now if we consider the map omega k, which is the composition of P. P is, in fact, the linear operator, linear projection of A to 1 onto the surface or the subalgebra generated by E1, E2 until En, which compose the biotogonal set in A to 1. And then if we compose sigma k with this P, which is a projection, we have an isomorphism of the FDS2 Banach algebra A to 1 into M2C. This means that this map omega k is a representation of the algebra A to 1 into M2 of C. Section 3, dimension of A squared equals 3. So here we don't take the same way as when we were talking about the dimension of A squared equal 2. We shall just remark that the algebras A to 2 and A to 3 that we have seen, their product can be decomposed in a way that can be generalized to products in the case of A to 3. But let me talk about a property of a subspace or of two elements in a Banach algebra, which is called the left pendulum property. You imagine that we have two pendulum that you, with the balls at each of one, you leave them and they collide, and one pushes another one at the left, because the product of the two is the left-hand side element of and we call this property the left pendulum property. In M3 of C, U, V, and W, which are written here, satisfy this condition. But it is the only case I know for this known algebra. But the algebra we are constructing here, this property is true for all subsets of this algebra. So, A22 and A23 I say that we can decompose the product, and the products are in relation 30 and relation 31. And we shall say that a Banach algebra is of type n when its product uh, looks like relation 30. And if we generalize this relation by saying that xy equal I equal 1 to 2 to n, j equal 1 to n, we have the Banach algebras of type n. And uh, if the product of A to 3, which is the xy in relation xy in relation 31, if we generalize it by saying that it is equal to I equal 1 to n, j equal 1 to I, fi minus j minus 1x, fj of y, ei, then we have Banach algebras type ATN. TNY because when we shall send this algebra in MN of C, it gives a lower triangular uh, matrix, lower triangular matrix. And we just need to make the verification in theorem 3.5. We studied the case A32, and after that the case AN2 for n greater than 3, and then the case 80 n for n greater than 3 by the relation we have seen there. And this gives the algebras satisfying dimension of A square equal 3 for the moment, but there are many others, and we need time to see them in detail in the future. Now, these are properties of these algebras, and we go to yes, this is the triangular matrix of what I was talking about. It appears here, and we go to section 4, which is an attempt of generalization of the algebras in section 2, dimension of A square equal 2, and dimension of A square equal 3. Okay, this generalization is not easy because we should normally dispose of a projection, the projection P, which appears in section 2 and section 3. We should have this at our disposal, but in a general Banach space, it's not possible to have such a projection on any closed surface of the same Banach space. This is a great problem, a bigger problem, because, and we want to go through this problem using, instead of a Banach space, a Hilbert space, because we know that in a Hilbert space, when you have a closed subspace, we always have the projection, orthogonal projection of the Hilbert onto this subspace, and we have a result in this direction, which is theorem 4.6. Theorem 4.6. Okay. If H is a Hilbert space, then for any proper closed subset E of H, there exists a morphism projection P from H onto E, so that the couple PE gives rise to a Banach projection algebra, which is, in addition, a Hilbert algebra. On this Hilbert space, we construct a structure of Banach algebra called a Hilbert algebra, admitting a unit continuous multiplicative linear form, and this Banach algebra is a Banach projection algebra. This is the last theorem, and I would like to thank you for your kind attention.
Okay, thanks for the very nice talk. Is there any questions?
Yes, please.
So these results that you spoke about, is it important that the algebras are Banach? Do you use the norm or
Okay. They could be just normed algebras, but
did you use a norm at all? Maybe, I mean, can you just use the setting of an algebra without the norm?
oh, I okay. Would I say that they could be just normed algebras, but maybe not just Banach algebras, because there are some things with topological problems that simple algebra without norm or something like that cannot do. But normal algebras, we can take that.
Okay, any other questions or comments? Okay, let's thank speaker again.
Right. Thank you very much.